So this is the first video out of 3 in a series on control that I'm presenting for the online winter school on spectral methods for complex systems. Thank you, Francesco, for the organization and for the invitation to participate. So this video will be on the variation of parameters formula, which is used in linear control systems. And it's a fundamental tool that is a basis for many of the methods used in control, both nonlinear and linear systems. So let's start with some definitions. First, a control system can be viewed as any dynamical system whose dynamical laws are not entirely fixed, as they are in problems of classical physics, but depend on parameters called controls, which can vary and with which one can control the behavior of the system dynamics. Mathematically, a control system can be written as a set of differential equations where x is the state, u is the control, and f is a function that characterizes the system dynamics and can also depend on time. Here, y is the observed measurement of the system, and g is a mapping from the state and control to the observations. In the linear case, the dynamics are written as ax plus bu, affine function of the state and control. Similarly, the observation map can be written as cx plus du, where a, b, c, and d are matrices which may also depend on time. Now, there are several different types of control functions that can be used in control system design. So the control is denoted as u, which lies in some subset of Rm, where u is the admissible control set and m is the number of control functions. So first, one can design feedback controls, which are closed loop, which map from some manifold M on which the system state X evolves to U. So there's a direct mapping from the state to the control. Then there is open loop control, where U is a mapping from time to the control space, and it is independent of the state at any given time. Finally, one can design a control which is a combination of both types. That is, the control may depend on time as well as the instantaneous state of the system. So here we'll focus on time-varying linear dynamical systems of the form shown here, where it's standard to say that the state is n-dimensional, the control u is m-dimensional, and the observation y is p-dimensional, with corresponding dimensions of the matrices A, B, C, and D, which are all linear mappings that are time-dependent. So this is the most general setting for linear systems. So there are several fundamental properties of control systems that we're interested in control theory. So first, controllability, meaning when can we achieve certain outputs? Second, observability. When can we deduce the initial condition from the output? Then there's a notion of realization. That is, can we construct a dynamical model that realizes a given input-output map? Also, we want to be able to do pole assignment. This is related to the Poincare-Lyapunov theorem. And the question here is, can we correct some undesired features such as instabilities by introducing feedback? Now, pole assignment refers to assigning the eigenvalues of the closed loop matrix of the dynamics to be negative so that the overall system is stable. We won't get into that in this lecture. Another fundamental property is the canonical realization. So what is the simplest model that describes a control system in terms of dimension? And finally, stability. How stable are trajectories of dynamical systems subject to small perturbations of initial conditions? Now, first, let's look at homogeneous linear systems. A homogeneous system is of the form x dot equals ax, and there is no control input. So this system depends purely on the state, and its solution cannot be exogenously influenced. Now, such systems have the property of uniqueness. That is, if all of the elements of A are continuous functions on a time interval, t0 to t1, then there exists at most one solution of the homogeneous system defined on that time interval when the initial condition takes on a given value. Now, this transition of the system state is characterized by the so-called transition matrix. So if the matrix A that specifies the dynamics has elements that are continuous on the positive real line, we can form a matrix phi as a function of t and t0 such that phi of t0 and t0 is the identity. And then we can write the state at time t as this transition matrix operating on the initial state. So what happens then is, differentiating, we see that the dynamics for x dot are A times the transition matrix times the initial state. So the transition matrix itself satisfies a differential equation phi dot equals A times phi. Now let's look at the Peano-Baker series. So this is a way of writing the transition matrix as an integral series, and it is related to the notion of matrix exponential. So if A is a scalar, or if A and the integral of A from t0 to t commute, then, so here we see this commutator, then we can express the fundamental matrix as a matrix exponential. That is, phi is the series where the matrix A integrated in time is in the exponent, similar to what we write for the exponential of a scalar. So for example, how can this be used? First, for diagonalization of a matrix. So if A is diagonal, then the exponential of A times T is going to be a diagonal matrix where each diagonal element is the exponential of the diagonal entry times T. Recalling that the exponential of a matrix is defined in this manner, if A is block diagonal, then the matrix exponential of A will also be a block diagonal matrix. Recall that a matrix is diagonalizable when the algebraic multiplicity equals the geometric multiplicity for each distinct eigenvalue. Now, also, suppose that A has n distinct eigenvalues. That we can write that A is P, D, P inverse, where D is a diagonal matrix, and P is a similarity transformation where V, I are linearly independent eigenvectors. Then we can write the matrix exponential in the following series, where we can move the similarity transform outside of the series sum and show that any matrix that has n distinct eigenvalues can be written can be transformed using the similarity transform P into the exponential of a diagonal matrix. Now, if P is any non-singular matrix, then we can perform this similarity transformation where we take the similarity mapping P outside of the exponential series. Next, I want to mention the Cayley-Hamilton theorem. So this is a fundamental property that if a matrix A has a certain characteristic polynomial, P of lambda, then the matrix satisfies its own characteristic polynomial. Recall that the characteristic polynomial, the solutions of the characteristic polynomial are the eigenvalues of the matrix. So let's now look at some properties of the fundamental matrix. First, at the initial time, so the transition between one time t0 and itself is characterized by the identity. Next, there is a composition property. So the fundamental matrix satisfies this transition semigroup property. That is, the diagram commutes, where the transition of the state between time t0 and t is given by the application of the fundamental matrix from t0 to t1, followed by the application of the transition matrix from t1 to t. Another important property is the Abel-Jacobi-Liouville equality. That is, if phi is the transition matrix for x dot equals a of tx, then the determinant is equal to the exponent of the integral of the trace of a. And it follows that the determinant of the fundamental matrix is always non-zero if the integral of the trace is of a is less than infinity on any finite time interval. And it follows that the transition matrix is always non-singular as long as the entries of A are continuous on the positive real line. This leads to the Baker-Campbell-Hausdorff formula. So given two matrices A and B, two square matrices A and B, we see that in general, the exponential of AT multiplied by the exponential of A sigma is going to be the exponential of A times T plus sigma. But in general, this property doesn't hold for products of matrix exponentials. That's because if you examine this matrix exponential, you see that here we have in the second order Taylor series expansion of the exponential, AB plus BA. Whereas if we look at the product of matrix exponential, we have in the second order term of the Taylor series 2AB. So these two expressions are equal if and only if AB equals BA. That is, if A and B commute. So this gives us the Baker-Campbell-Hausdorff formula. So if A and B are square matrices in Rn by n, then there exists a C in an n matrix C such that exponential of A times the exponential of B equals the exponential of C, where C is given by the series of Lie brackets, and where this bracket of A and B is called the commutator. Now, let's see what happens with the fundamental matrix under a change of coordinates. So let's examine the system x dot equals ax with the fundamental matrix phi a, where a is square and x is in Rn. Now let's consider a change of variables transformation. Z equals p times x, where p is the similarity transform, and for which we assume that p dot, so the derivative exists, and the inverse exists. So it's an invertible linear mapping. Now we wish to find the fundamental matrix phi z for the system in the transformed coordinates z. Now because P inverse exists, we have x is equal to P inverse times z, and x at T naught equals P inverse T naught times z of T naught. Differentiating this expression, we see that z dot equals P dot x plus P x dot. And working through, we see that we have a similarity transform of A plus some function of the derivative of P and P inverse, the product. So the transition matrix for Z, let's call it phi A tilde, where A tilde is given by PA P inverse plus P dot P inverse. So together with Z naught, which is the transform of x naught at time 0, we therefore have that x is equal to a similarity transform of phi A tilde times the initial state. We can conclude that phi A has this form. And thus, we see that the diagram commutes. So if we go from the state x at t0 with the similarity transform to z, then we can apply the fundamental matrix and the transformed variables to get z evolved to time t. We can invert the similarity transform to get x at time t, and likewise invert the fundamental matrix to get back to x at the initial state. Now, let's look at what happens when we have a non-homogeneous linear system. So here, we go back to a control system where we include the control u of t, where A is an n by n matrix. B maps the M controls to their influence on the state, and X is the state, U is the control. Now we recall that we denote by X the general solution, XH the homogeneous solution, and XP the particular solution. And we want the particular solution. We get this using the variation of parameters formula, which is given as the solution to the non-homogeneous system, and is given by applying the fundamental matrix to the initial state and adding this term that integrates the influence of the fundamental matrix on the input control multiplied by the mapping B. So the derivation is as follows. The solution, again, is given by this formula. And the idea here is that for a system, z dot equals f of t, we can integrate to obtain the initial conditions plus the integral of f over the time evolution interval. Now, we can let z be equal to the inverse of the fundamental matrix of x of t. So this would mean that x is the evolution of z. Rather, x is going to be the evolution of the dynamics specified by x dot equals ax, the homogeneous system, starting with the initial state z of t. Differentiating this expression with respect to t, we have x dot equals phi dot z plus phi z dot. Now, if we equate a of tx plus b of tu to a times phi z plus phi z dot, that is x dot, because x dot equals this expression in dynamics. This will give us that z dot must equal phi inverse times bu. Hence, we can write that we see that substituting for f of t, we see that f of t is given by the expression inside the integral. Recalling that the fundamental matrix multiplied by its inverse is the identity, and therefore that x of t is equal to phi times the initial state plus phi times the expression inside the integral. And we can actually bring this fundamental matrix inside the integral to give us, since it's independent of sigma, and this gives us the final expression. So that is the variation of parameters formula in linear control systems, the general solution to non-homogeneous linear equations. You'll find the description of this and many more very useful linear systems properties in Finite Dimensional Linear Systems by Roger Brockett. There's a recent republication of the original that was issued in 2015. Thanks for your attention.